What we're going to do now is determine the acceleration of a rolling sphere, and that is rolling without slipping, by three different methods. The first method is the conservation of energy method. Now we have the moment of inertia of a sphere is 2/5 mr squared, mass is m, radius is r, and this would have to be given to you. Even the AP Physics C kids would have a difficult time deriving that moment of inertia. And what we have is we have the bottom of the sphere. If this is distance x, this height that will be from the bottom of the hill, we can call this h. We can call this x sine theta, if that is an angle theta. And either one is good. We are going to determine this to start with using conservation of energy. And just recall that the height from the bottom of the hill to where the bottom of this sphere is the same as from the center of mass where it is now to where the center of mass would be later. So that height is the same. I'm just going to use the height from there to there because it's easier to see geometrically. Now let's go ahead and use energy conservation to figure out what's going on. Of course, our generalized energy conservation equation is going to be E initial plus work non-conservative equals E final. Now, we will find out, or I guess we'll find out right now, that friction, even though there actually is a force of friction here, it is going to do no work. Because what happens is, this point right here is actually motionless. When this rolls, this next point right there will just kind of set down like a foot right there. This next point will kind of set down like a foot right there, and there will actually be no scraping or dragging. So if it was kinetic friction, it might do some negative work. But in this case, rolling without slipping, although friction is a force and it will reduce the acceleration, it will not do any work on this sphere, because there's no displacement at the point of contact where friction's acting. This thing isn't dragging or moving at all. It's really just like it's just setting down there each time. That sets down there, that point would set down right there, that point would set down right there. It's like putting your foot down and then lifting it up. No work is done by friction in this case. So I can just get rid of this. There's no work non-conservative. What form is energy start off in? Let's go down here and find out here. So it's going to start off in the form of gravitational potential energy. So I'm just going to take my E initial is going to be just mgh. And what form is it in finally? When it gets down here, it is going to be moving translationally. The center of mass will have a velocity this way via the center of mass. But it will also be spinning rotationally. Omega. So it's going to have both translational kinetic energy and rotational kinetic energy. Again, both are in joules, both are kinetic energy, but it's manifested in different motions. So let's go ahead and list both of those. mgh will be the kinetic energy translational 1/2 mv of the center of mass squared, and that's the final speed when it reaches the bottom, plus 1/2 I, the moment of inertia, omega squared. Because it's going to be both moving translationally and spinning. So using this method, all we got to do is solve for VCM final. But you may say, wait, there's more variables here than we can solve for. Let's say we're given M, we're given G. By the way, M won't even matter. We're given this H right here. We're given nothing else, but we will have to be given the mass and the moment of inertia. Seems like there's too many variables, but let's go ahead and just simplify this a little bit more to see if we can reduce the number of variables. mgh will equal 1/2 mvcm squared. Is there any way we can express this omega in terms of the velocity to the center of mass? Well, if you're getting used to this stuff, then you'll know that we sure can. This will just be 1/2. I is 2/5 mr squared. And omega we can express as v of the center of mass over r. Of course, we can't forget to square that whole thing. Now, the first thing you got to notice, and this is why we always solve symbolically, is the mass doesn't matter. Spheres of any mass will roll down this thing at the same speed.
And acceleration.
Doesn't matter what the mass of the sphere is. So that's the first thing we find. And then let's see if we can simplify this further. GH is equal to 1/2 VCM squared plus, this is going to give us 1/5 of R squared. But let's check this out. We're going to get VCM squared over R squared. Hey, this squaring of this R, I'm just going to get rid of that and rewrite that like that. This is going to cancel that. So notice that I get, that'll be 1/2 and 2/5, 1/5 VCM squared. Hey, check it out. Not even the radius matters. The mass doesn't matter. The radius doesn't matter. All spheres are going to tie in this race. So then we can just go ahead and solve this for VCM. Let's go ahead and express this in terms of x and theta. So that'll be GH, or G times x sine theta, will be equal to 7/10 and VCM squared. So I'm going to put this all on one side, and you'll see why in a minute. So notice that we get 10/7 G times x times sine theta equals VCM squared. But what I'm after is the acceleration. Luckily, we have an equation that'll help us with this. Now, if I've got the final speed, how can I find the acceleration? Well, I'm given x, I'm given the distance, and I've got the final speed. What will give me, and what's the initial speed? Initial speed is 0. V initial is equal to 0. So that means that, let's do it like this. Because we know that V final squared equals V initial squared plus 2AX, I will just use x here because it is delta x, the same thing.
In this case.
Well, this V final, this is the V final right there. I'm just going to put that in right there because this is the same thing as VCM squared right there. So that'll give us this. 10/7 GX sine theta is equal to, this V initial squared is 0. It's just equal to 2AX. Hey, check it out. Canceling this out, that doesn't matter. We got to divide both sides by 2. So that'll give us, get rid of that, and then we'll have 5/7 over here. So what we're ending up with is 5/7 G sine theta is equal to A. Notice what is conspicuously missing from this. The mass doesn't matter. The radius doesn't matter. All spheres will accelerate down a ramp without slipping at A equals 5/7 G sine theta. Pretty cool.